you. Okay, good afternoon, everyone. So what I'm going to run through here is a quick topic, a quick discussion on embedded vision solutions for industry. We're going to talk about some of the usage applications, some of the technologies involved, and some of the implementation choices. And then we're going to focus in on more of the industrial options available to you, from smart cameras to embedded vision systems, and then end up talking about some software and integration considerations that you should definitely think about before you buy a vision solution. Okay, so some of the slides I may whisk through rather quickly, only because from a time perspective, but I think they're all available online, so it shouldn't be too problem. So embedded vision is a term that we hear a lot about lately, but the reality is it's not new. It's been around for many, many years in industrial vision. The term itself implies the integration of vision technology in any application. And so even though the term itself is not new, the expansion of applications over the last 5 years is. And we see, like, whether it's in automotive or security or sports or biometrics or social media applications, the adoption of vision technology is very widespread. And that is driving advances in technology that ultimately will benefit everyone, and certainly us who are working in the industrial sector. So looking at the kinds of technologies involved here, they're fairly straightforward. Sensing, obviously you take pictures, you process pictures, and software. There's all kinds of different sensors available. We manufacture a bunch of sensors ourselves. But you can buy board cameras, you can buy cameras, you can buy plug-and-play cameras, Geraghty Vision, USB 3, camera link. You can buy board computers, embedded systems with gigabit Ethernet connections, and you can buy any kind of software you can imagine. So you can pick your operating system, you can pick your programming language, and you can work off whatever library choices you have. So you can use OpenCV to get started, or you could use a more prepared library, for example, from Stemmer Imaging for common vision blocks. Or you could use a turnkey application like Sherlock that we manufacture, right? So that's a product that will allow you to implement your complete vision solution without having to do any programming. So if you're contemplating making or purchasing a vision solution, here's some considerations. One option is to do a complete design from the ground up. So if you do that, obviously the time to market or the time to the solution is going to be longer. Your engineering budget has to be quite big, because it's going to take some number of engineers to implement. But at the end of it, you're going to have a fairly low runtime cost. So if you have high volume, this is a good option. If you don't have the time or the engineering budget to develop that, you might want to use a semi-custom approach. That way you can buy some pre-built components, cameras, vision boxes, software, and sort of piece them together and make a solution for yourself. So the advantage of this, of course, is quicker time to market, but maybe the support is a little bit more intense, because you have to deal with multiple suppliers, and you have to, the support angle could be a little bit more than you bargained for. So and the third option is off-the-shelf components. So these are the components that we as a manufacturer make. So you can buy smart cameras or vision systems and or software and cameras, and you can develop the application very quickly. So this approach is probably the easiest and the fastest to implement. And the downside perhaps is the runtime cost is a little high if you've got some volume. But as we go through these options for you today, you'll see that the prices are actually not as different from developing your custom solution to buying an off-the-shelf solution now. So manufacturers like to categorize things by product, and we are no exception to that. I try to keep it pretty simple, so I look at products in terms of what they do. So there's point inspection products. So these are products that are looking at one thing, one image, and rendering a result based on that image, right? So these are point inspection products. It's the concept of distributed computing. So you can put lots of different smart cameras on the line. Each of them are doing a very unique job, and we're distributing the processing across all of those cameras. Right? The other option is multi-point solution. So you have an embedded vision platform, for example, that has multiple cameras attached to it. In that case, you have a centralized processor. It's doing all of the processing from images from all of the cameras at the same time. Right? So there are pros and cons of both, and we'll sort of look at those as we go through the products. This is a little wordy, so I'm not going to spend much time on here, but there are certain advantages of using distributed technology. Generally, they are easier to integrate, easier to set up, and easier to support, right? Because you're only looking at one particular thing. So if you have lots of cameras on a line and you need to change one function, you just touch one camera and then you're done, right? On the flip side, centralized processing, you have more flexibility, you have higher performance, right? And ultimately, you can have a very low runtime cost. So if you have a system with 16 or 32 cameras, which is not unusual, attached to it, your cost per camera is very low, right? So you have to look at the different cost aspects of both solutions and figure out which one makes the most sense. So we're going to spend a little bit of time looking at some of the technology options available, off-the-shelf options. The first one is vision sensors. These are relatively low-cost solutions. They are designed to do specific tasks very well. So they may be low cost, but they're not. It doesn't mean that they are not a good product. It just means that we only expose certain features of the product for different applications. Ease of use is very high on these kind of products, so they're easy to set up, easy to adopt. Typically, the resolution is quite low, so we're talking about 640 up to 800. You may get a 1280 sensor once in a while. They all have integrated lenses. M12 lenses are quite common. Some have autofocus lensing. They all have sort of integrated lights. So these light rings are good in some applications, not so good in other applications, right? So depending on your need, they might be a good solution. But they're generally well priced. They are, typically in the 800 to 1200 euro range. So it's a nice solution if you have low quantity. What do they do? Well, I categorize these into two groups. Well, first is error proofing. Error proofing, you're doing basic checks on parts or assemblies. You're checking the presence or absence of things. You're looking at features. You may be checking the color to make sure the color matches. They are general sort of assembly verification checks. And the other is identification. So all of these barcode readers, matrix readers, OCR character readers, these are all examples of vision sensors, but they are programmed to be specific products for identification. Usually you don't see a crossover between the two at this price point. You'll see a function set for error proofing or a function set for identification, but you won't see a combination of the two. You might see suppliers like us, for example, we'll offer a low-cost version of an error-proofing sensor with 2 or 3 functions, and then you can pay a little bit more to get maybe 6 or 7 functions, right? So then we move up to smart cameras. Smart cameras are also called single-point vision systems, right? So there's the terminology of some of these solutions is kind of confusing, but a smart camera generally gives you incremental performance for a little bit more cost, right? So I like to say that it's maybe twice the cost of a vision sensor, but you get a lot more functionality. So whereas before with the vision sensor, where we broke down the error proofing and the identification functions, you tend to see all of those available inside a smart camera. The nice things about these is they have different resolution choices, so you can get up in quite high resolution. 5 megapixel is quite common nowadays. They have better optics. Most of them have C-mount lenses. They don't typically have integrated lights because most of the high resolution applications need external lighting, correct, to get better contrast on the images. But they're also very quick to set up and very easy to integrate. All of these products you've seen so far will have the factory protocols built in, so you can quickly connect up to Profinet or Ethernet IP or PowerLink or CC-Link or any of those kind of protocols. So a little bit higher cost, still ease of use, and quite flexible. And this slide just basically emphasizes what I just talked about. Better sensor options, more flexibility in terms of the application, more performance. So a lot of these smart cameras will combine different processing elements like CPUs and DSPs and maybe GPUs and FPGAs to give you the performance you need, and of course very good usability. Okay, then we get into 3D sensors, specifically line profile sensors. So whereas like a vision sensor will operate on a two-dimensional XY image, a 3D sensor will operate on a two-dimensional XZ image, where Z represents the height. So these products are quite good. They generate an image based on the profile of a laser projected on a part. So you get a height profile or a shape profile, and they make height measurements and shape measurements. So things like angles and distances and heights and things of that nature. They're pre-calibrated, so they work very well in a fixed distance from a part, but they're also tolerant of some depth of field variation, right? So what you do is if you move your part within a certain range, you're still going to have the exact same height measurements, but you may lose some of the X resolution. Some of these products I've seen claim to have like 1 micron height resolution, which is extremely aggressive and I think unachievable in many cases. But if you do see products with 5 to 10 micron resolution, they're very good. One thing about this is the cost is quite high. So if you compare like a vision sensor at 1,000 euros, for example, a entry-level 3D sensor is probably on the €5,000 range. Here's some typical applications. We see a lot of these kind of applications in automotive or in wood manufacturing. So typical application is there. We have two surfaces and you want to measure the gap between them. So these could be upholstered surface on the windows of a car, the inside windows, or they could be gaps between doors or panels on a car. And it's very easy to sort of use this product and measure the gap and just move the sensor across the gap to make sure it's consistent. And a lot of usage is in automotive for that. Similarly with wood, you might want to look at the shape after the wood has been cut, or you might want to look at surface defects like holes or knots or things like that. And these products are very good for those kinds of applications where 2D products would typically fail. These products can also be used as a camera, because in some applications it's not convenient just to look at the profile. You want to look at the whole surface, right? So what they can do is they can output these profiles very fast and catch them in another embedded computer somewhere and generate a surface, and that surface can be inspected from 2D tools. So for example, this weld application where you have the height varies and the width varies quite a lot. If you want to look at the porosity of the weld, for example, these are the holes that are in the weld, you might be better off doing that with 2D tools than 1D profile. So the camera could output a surface for you and you can use 2D tools on that. Okay, so we won't spend much time here. We talked about this. One of the nice things about these is they operate independent of color and contrast. So everything we talk about in imaging, it relates back to the optics and the lighting associated with it. And these products are sort of tolerant of all of those things, which is very nice. Okay, vision systems. These are effectively PC systems, if you will. People always say to me, well, PC systems are sort of on the way out. They're long in the tooth. They're Windows systems. We don't use them too much. But the reality is they're extreme high usage. In fact, probably over 50% of our business uses embedded systems like this. The advantage of them is that they're very flexible. So you can add any kind of camera or a sensing device to it. And we make a bunch of different sensing devices, but but what's nice is you can do line scan applications, area scan applications, microbolometer, which is a long-wave infrared application. You can do X-ray, you can do 3D, and you can hook all of these cameras up to one box and one piece of software, and you can develop your system that way. They're very convenient. They've got lots of storage, they've got lots of processing power, you can mix and match things, and if your requirements change, or you can adopt or adapt the system to change with that. So you get that flexibility, performance, and the price is not too much different. If you add lots of cameras to these things, the price per camera goes down dramatically. So 5 reasons to choose PC-based systems are pretty obvious. Flexibility, performance, because you align with PC technology, that's going up every day, and you're going to ride that wave. Usability, everyone uses PCs, they know, they're familiar with them, the look and feel is familiar. Lots of memory, lots of our customers like to store lots of images, and this is not possible on a smart camera. And even though you can do that over a network, it tends to be slower, right? So having the memory local is important. And the fifth one is there's no other option, right? And that's important because I see a lot of customers who try to go down this path of using a smart camera to solve a problem at all costs. This is what they're going to use, this is what they've selected, and they get to the end and they realize it's not possible. So they have to go back to this kind of design. A variant of a PC system or embedded system is a supplier lock system. And we don't actually, or we haven't made any of these systems to date, but we are certainly in the running to make one. And what they do is they allow us as a supplier to add capabilities that are unique to our product line. What it means to you is you have to work with a single supplier and you have to use products by that supplier. So you use cameras that work with our system, software that works with our systems. And so you may find that that's a limitation, but the reality is you're getting the same kind of product, but you're getting more capabilities in that product for your needs. So when we do this kind of solution, we can expose what we feel we need to expose for you as a user. We make those decisions for you, so you may think that's not a good thing, but sometimes it is. So. Okay, so onto the software requirements. So this slide is kind of important because if you've looked at different software packages, one thing you'll know is no software is created equal. And there are 3 things that you need to keep in mind. The first is who's going to program it, what's it going to interface with, and who's going to use it, right? And they're very different requirements, especially the first and last requirement. Because an engineer will take a product, like our product, for example, Sherlock, and it's a great product, and they're going to be able to do whatever they want to do with it, generate programs and different solutions. But the operator is going to have a very different look and feel in order to use that on a factory floor. So the software has to be adaptable. It has to give you the option of different interfaces to build your own interface or use an interface that comes with it. And it has to seamlessly attach to these devices that are in the network of the solution you're developing. On the integration side, you have to really think about where you're going to put this device. Does it have to be protected? Is it likely to be knocked by a robot or something else, right? So you have to consider the environment that it's going to be put in. If you put a PC with a fan in an environment that's got a lot of humidity, you're going to have some problems, some reliability problems. Do you have the correct lighting and optics, right? This is always what you hear with vision, right? So lighting will make or break a vision solution. Even though the vision tools themselves are more robust now and more adaptable to different lighting conditions, you still want to make sure you spec in the right technology to do the job. Does it communicate? We talked about factory communications, but what about the guy that's 1,000 miles away who wants to remote into the to the production line and see what's going on, right? So does it have the remote connection capabilities you're going to need? How do you interact with the system at runtime? Operator interface we talked about. Is the system going to change, right? Is it possible that after a few months you have a new part that you want to inspect and that system is no longer capable of doing that, right? Have you planned for that expansion? It's very important. And finally, what is the ownership cost? And the ownership cost is how long is it going to take you not only to implement it, but to support it? Who are you going to have to train? What happens if the guy implementing it leaves? Who's left holding the project, right? So these are all kind of factors to consider when developing vision systems. Okay, so in summary, embedded vision is everywhere we look. It's not just a ARM processor or a board camera. It's used extensively everywhere, more and more every day. Consider the pros and cons of make versus buy. I try to encourage people to look closely at the pre-built solutions before they go off and invest in their own design. Distributed processing versus centralized processing. We talked about that and what the pros and cons of each of those are. Select the product that best suits the application and the user requirements, right? So it's no good if you've got a very easy to use engineering front end, but then the guy on the floor doesn't know how to use it. And lastly, software is really, 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 really important. In my business, we develop a lot of hardware, but in my location in Boston, in the US, we develop mostly software. So we develop a couple of different software packages, and we invest a lot of time and effort in that. And there's a good reason, because the hardware may look great, but if the software isn't great as well, then you're going to run into some problems. I think that's it.
That's it.